I'm Ethan Manilow. I'm currently in the process of finishing up my PhD in the Interactive Audio Lab at Northwestern University, where I work with Brian Pardo. I also work part-time as a student researcher on the Magenta team at Google Brain. And I want to, before I start, thank Elio, Sertan, and Ken for inviting me and organizing this talk series. And now let me talk to you a little bit about musical scene analysis and generative modeling. Before I do that, I kind of want to step out, zoom out a little bit. And over the course of human history, we as a species have spent a lot of time and energy developing technology just so that we can make music. And each type of musical instrument doesn't just enable new ways to create music, but it also brings with it new ways to conceptualize what music is. And today, myself and other researchers are looking to the new step in this lineage, which is machine learning systems. And so the question is, how can machine learning systems create new types of interactions and new types of music? Well, if we're thinking of machine learning as an instrument, then the first, most obvious way that it fits in is that we want some kind of system that can generate sound based on some input controls. And this is similar to how we normally think of musical instruments: turn a knob, change the sound, etc. But machine learning is malleable, and we can use these same tools to listen and analyze music in sophisticated ways, enabling us to understand music in ways that were either difficult or impossible beforehand. And furthermore, we can ask those analysis models to use what they've learned to assist our sound generation models. And this is kind of the core of what I'm going to talk about today. These paradigms have fancier names. So in machine learning, the process of creating data like musical audio is called generative modeling. And similarly, I'm going to refer to the process of analyzing a piece of musical audio as musical scene analysis. I'm going to give you some more in-depth definitions in just a moment, but I want to make the case that these paradigms are not mutually exclusive. Ideas for one can be used to further the goals of the other, and vice versa. In this talk, I'm going to showcase projects spanning both generative modeling and musical scene analysis, and the theme that's going to run through all the projects is that ideas from generation and analysis will be blended together to accomplish the goals of the project at hand. So first, let me quickly provide a definition of generative modeling. Let's say we have a set of recordings of violin excerpts, and we can think of these excerpts as existing in some sort of space. For example, the space of their waveforms as a collection of audio samples, or maybe the space of notes. And these are just three of many possible examples of plausible violin excerpts, which are shown on the many dots on screen. And we can say these examples are drawn from some probability distribution P data with a D. This probability distribution is the underlying distribution of all possible violin excerpts. And because there are nearly infinite number of ways to alter a violin excerpt, think of recording it in a different room with different reverb, changing a note, changing the articulation of a note. So this underlying distribution is, for all intents and purposes, unknowable or intractable to compute at best. In generative modeling, despite this, we want to make a model P theta, the Greek letter theta here, that approximates this underlying distribution given only the set of examples in our data set, which were all the dots in the earlier slide. So when this model is trained, we can create new data by sampling from this distribution that the model learned. And in this case, we get a brand new, never before heard violin excerpt. So in summary, in generative modeling, we want to learn some model that approximates the distribution of our data, and then we sample from that model to create new data. Later in the talk, I'm going to discuss the ideas that musical scene analysis will borrow from generative modeling, specifically the idea of sampling, as well as some neural network architecture, some generative modeling, and entire pre-trained models. Now let's move on to defining musical scene analysis. Musical scene analysis is a subset of machine learning specifically targeting musical audio. This is sometimes called machine listening, but I like the term musical scene analysis because there are things specific to music that we want to analyze. And to that end, the goal of this field is to identify and locate these key aspects of music that humans attend to when they listen to songs. So some common musical scene analysis tasks include things like automatic music tagging, fundamental frequency estimation, automatic music transcription, and source separation. Later in the talk, I'll discuss one transcription project and two source separation projects, and I'll give more details about these tasks when I get to them. But the key takeaway here is that these models aren't creating new data like a generative model. In fact, they're producing a more compact and therefore more lossy way to represent audio data in a way that emphasizes features that we care about for the task that we're trying to accomplish. For instance, an automatic music transcription might convert a high dimensional audio file into a low dimensional note sequence such as MIDI. But again, more on that in a few minutes. Okay, so now we have some basic definitions for generative modeling and musical scene analysis. And I promised you that I was going to talk about some recent work where both of these ideas are blended together. So in total, I'm going to give an overview of 4 projects that do just that. They take ideas from one of these domains and apply it to the other. So first, I'm going to jump right into MIDI DDSP, which is a generative model for musical audio. Most generative modeling for music results in models that directly output audio waveforms, offering little control, if any. If we're lucky, the generative model let us convert a set of notes into audio, but there's still not a way to make edits to how these notes are performed. However, for musicians, creating music is not a one and done, zero-shot process. We want to be able to control specific aspects of the performance. Let me give you an example of the type of control I mean. In a second, I'm going to play for you a violin excerpt from Phantom of the Opera. And just so you can follow along, here's the musical score. Here's a spectrogram visualization of the audio of the violin. And here's the pitch contour of the violin playing. So here's what this violin excerpt sounds like. Now let's say our violinist wants to make edits to their initial performance of this excerpt. For instance, they can make low-level edits like adding a pitch bend between the first and the second note shown in yellow. They can change how the notes are played, like adding more vibrato in the second note and changing the articulation on these descending notes shown in green. And finally, they can change the notes themselves, like shifting up these last two notes up an octave, shown in blue. Let's hear what all of these edits sound like. And here's the original audio again. So these are the types of edits that musicians want to be able to make when they're making music. So the question is, how can we make generative models that enable these types of controls? As a matter of fact, both of these excerpts that were output by our model made a DDSP. So let me dive into how this works. As you just heard, MIDI DDSP can turn a musical score into a realistic sounding synthesized performance while also enabling detailed control of that performance. The MIDI DDSP model itself is actually 3 models that form a structured hierarchy. And each of these 3 models I'm going to call a module, and they allow manipulation at different timescales. Each of these modules does its own form of analysis of the audio signal to provide the controls that we use when we generate audio. So I'll first talk about this audio synthesis module. As you can probably guess from the name of the project, the audio synthesis happens with DDSP components. DDSP stands for Differentiable Digital Signal Processing and allows neural networks to learn how to synthesize audio by manipulating a simple set of DSP elements, such as a pitch contour, amplitude, harmonics, and noise components of a single note audio excerpts. These four elements are called the synthesis parameters, and they happen 250 times a second. What's happening here is the neural network has to analyze these elements of the music so that it can synthesize them. The original DDSP autoencoder used in MIDI DDSP is what's called an analysis by synthesis module. So let's move on to the next level, the note expression module, where we transform these low-level synthesis parameters into a set of high-level note attributes. As I just mentioned, the raw DDSP synthesis parameters are very high-dimensional, and because of this, in MIDI DDSP, we want to extract a set of summary statistics that determine the expression of each note, yet another analysis step. So we define 6 summary statistics that are analyzed from these synthesis parameters and dynamically pooled over the duration of the note, where we're left with 6 controls that occur once per note versus 127 synthesis parameters that happen 250 times per second. So then to generate these synthesis parameters from a set of note expressions, we use an autoregressive RNN and a GAN for different parts of these synthesis parameters. If you want to know more details, I implore you to read our paper, but here I just want to look at one of these note expressions to get an idea for how it works. So we'll look at vibrato, which describes the amount of oscillation or wobble in the pitch of a note. In MIDI DDSP, we set these values for each note. So here we can set a vibrato at 36% for the first note and 82% for the second note. And we can see that the amount of oscillation in the pitch contour of the first note is smaller than the second. We can also set these values very low to turn them off completely. And notice how there's just one control that lasts for the entire duration of the note, no matter how long it is. The final piece here is the expression generator, which will generate performance characteristics by controlling those note expression summary statistics I just described. Because the previous note expression module does most of the heavy lifting in converting these expressions to DDSP parameters, the generation of these 6 expression controls per note is relatively simple. Here, we just used another autoregressive RNN to predict values for each note. One of the cooler things we can do with MIDI DDSP is combine it with other models. Here, we're going to take this familiar note sequence. And we can give it to Coconut, the model behind Google's Bach Doodle. CocoaNet will write 3 additional note sequences that harmonize Ode to Joy in the style of a Bach chorale. We can then synthesize each of them with a set of MIDI DDSP instrument models, resulting in a MIDI DDSP quartet. Every aspect of the audio that you're about to hear, other than the original melody, is composed, performed by machine learning systems. So let's hear what the ensemble sounds like. Okay, so that's MIDI DDSP. It's a generative model that combines realistic synthesis and expressive control. And if you want to hear more, the lead author, Yusong will be presenting it next month at iClear. But as I was describing MIDI DDSP, I pointed out parts of the model that relied on some kind of analysis. However, there's one important point that I omitted, and that's that MIDI DDSP needs to be trained on single instrument audio with aligned transcription data. And that's, for instance, why the ensemble was so out of tune, because we could only find that's the only data we could train it on. But most audio has multiple instruments and doesn't come with aligned transcription data. So how do we get it? So we'll talk about isolated instrument data with source separation a little bit, but for right now, let's talk about getting transcription data using MT3. But actually, before I dive into MT3, let me just give you a definition of what automatic music transcription is. So automatic music transcription is the task of converting an audio signal into a human-readable musical score, or a transcription. This is the musical analog to speech recognition systems that turn recordings of human speech into text data. And an example of transcription is shown at the bottom, where we have a transcription system turning the yellow bass guitar into a piano roll format. I like to think of transcription as the opposite of playing a piece. When you play a piece, you turn a set of notes into audio, and when you transcribe a piece, you turn audio into a set of notes. So let me set up the automatic transcription world as it existed before MT3, going back a few years to a project we did called Cerberus. Cerberus is actually a source separation network that we modified to do both separation and transcription. And again, I'm not going to go into the details of it here, but the important thing to know about Cerberus is that it's a very straight ahead analysis model, uses an LSTM for one-shot inference without any kind of sampling process like what you'd see in a generative model. The other thing that's important to note here is that the output instruments that Cerberus is going to predict are fixed. So if we wanted to do piano, bass, guitar, drums, we would have to train one model to do that. And if we wanted to add another instrument, we'd have to train a completely new model. So really quickly, we're going to listen to some output of the Cerberus, where you're going to first hear the song, which is a mixture of a guitar and a piano. And then you'll hear some source estimates for the guitar, which will then fade into the resynthesis of the estimated guitar transcription. You'll also see the piano roll transcription on the screen. And then the sequence will repeat again for the piano transcription and separation estimates. Here we go. Okay, so it's cool that Cerberus can separate transcribe, but honestly, the output could be better, especially that piano. And furthermore, as I mentioned, the instruments that it supports are fixed. So once the Cerberus model is trained, you cannot ask it to separate or transcribe a new instrument without either retraining the whole model or expecting some really funky results. So that big piano and guitar model cannot transcribe a saxophone or a drum set without a whole new retraining process. So this brings us to MT3. And this project is led by Josh Gardner and Ian Simon at Magenta. MT3 stands for multitask, multi-track music transcription. And one of the ideas behind MT3 is to use an encoder-decoder transformer architecture. Transformers are a neural network architecture used for generative modeling, most commonly on language tasks, but they're also starting to see use in vision and audio and vision tasks. And probably the most famous example of a transformer is OpenAI's GPT-3 language model. The insight behind MT3 is that we can treat a transcription as a sequence-to-sequence task, where the input is the spectrogram, which we can treat as a sequence of spectral frames, And the output spectrum, we input the spectrogram into MT3 transformer model, and the output is a sequence of tokens that look a lot like MIDI events. Because the encoder-decoder architecture is a generative model, it has a sampling process. But instead of sampling new data to mimic our input distribution, we sample transcription tokens from a vocabulary. This vocabulary is designed to mirror the MIDI specifications with specific token types indicating the instrument ID, MIDI note number, timing of events, on-off indicators, etc. So a set of tokens actually is the transcription, which can be stored as MIDI or in the piano roll format. One of the main appeals of this vocabulary is that we can now train MT3 on any data set we can get our hands on, and the only limitations of the output is the data that we have. So this allowed us to train an MT3 model on every transcription data set we could find all at the same time. And we compared this model to other models, including Cerberus and the commercial software Melodyne. And in this graph, MT3 is blue and higher values are better. And so clearly MT3 is able to take advantage of its training data and get better transcription performance than any system we're aware of. So let's listen to the same piano and guitar duet and compare the output of Cerberus and MT3. This time we're only going to listen to the transcription outputs. And first you're going to hear the mix, and then you'll hear the Cerberus transcription results while the piano roll is shown on screen, and then the same sequence will happen for MT3. But before I play the clip, let me just explain to you what to listen for. So first you'll hear Cerberus do a great job transcribing the guitar part and an utterly horrible job with the piano, as we just heard. And then you'll hear MT3 miss most of the guitar notes, but then it's going to do a near perfect job transcribing the piano. And I'll talk more about this after I play the example, but for now, let's listen. So now we're going to hear the MT3 results. This is where the guitar would be. Okay, so as I just saw, Cerberus did a better job transcribing the guitar part, but it turns out the MT3's instrument flexibility is also its main weakness. Sometimes it doesn't know how to determine the correct instrument. So in this case, it thought it heard a violin instead of guitar, and actually you can hear most of the guitar line is transcribed in the piano output. So this issue with predicting the right instrument label is one of the most obvious failure modes of MT3, and it's one that we're currently working on. However, zooming out a little bit, the MT3 transcription got almost all of the notes correct if you ignore the instrument labels for a second. And the MT3 piano transcription captured the overall gestalt of the piece and sounded really like a plausible transcription. So that's kind of the good and the bad of both of these architectures, right? So MT3 is flexible enough to support all these different instruments, but it can't keep the instruments straight. So in summary, MT3 uses an encoder-decoder transformer to do automatic music transcription. And not only is the neural network architecture borrowed directly from the generative modeling world, but we're also sampling from a vocabulary that lets us to train on many possible data sets. Again, this will be presented at iClear next month. So if you want to hear more, be sure to check out Josh's presentation. So now I'm going to turn to the first of two source separation systems that I'm going to talk about. And this one is called TagBox. But again, before I get into TagBox, let me first describe what source separation exactly is. So when I talk about source separation, I find it's helpful to first think about how music is recorded. Typically, when musicians make a song in the studio, they record each instrument by itself in isolation such that each instrument has its own track. A mixing engineer then combines all of the instrument tracks into the version of the song that we hear on the radio, and this is a process called mixing. Source separation is the opposite of this. We're going to start with the song we hear on the radio, and then we want to do some kind of magic to get these original isolated instrument tracks back. So if we just look at the guitar, what we really want to do is effectively mute all the sounds that are not guitar sounds. So one of the problems with music separation is the data sets that we have are small. The standard data set, MuseDB18, is on the left of this chart, and Slack 2100 is just to the right of that. If we compare these to speech separation data sets, our standard music data sets look tiny. And speech has much less data, much less diversity than music data, one might be able to argue. And on that note, let me talk a little bit about data diversity. So while the MuseDB18 dataset contains recordings of live musicians, it only supports 4 source types: vocals, bass, drums, and this catch-all 4th source type called other. And on the other hand, Slack 2100 has support for 34 source types, but all of the audio in it is synthesized. So it's not clear how a model trained on it will generalize to recordings of live musicians. So how do we get access to models that have been exposed to more data? And by more data, I mean both in terms of raw hours of data, of audio data, and more source types. This is the drive behind TagBox. TagBox is a separation system that combines OpenAI's JUKEBOX and a music tagger. I'll talk more about each of these pieces in a second, but hey, would you look at that? A generative model and analysis model working together. All right, let's talk music tagging. Music tagging is the task of predicting a set of tags from raw audio signals. These tags should have semantic meaning, like genres or moods, or indicating if a particular instrument is present or absent. The music taggers we're going to use are all convolutional neural networks, but let's talk about a big reason of why we want to use music taggers in the first place, and that's data. Again, I'm going to show you the same 2 separation data sets as before, MuseDB and Slack, and if we compare these to music tagging data sets, it's clear that tagging data blows separation data out of the water. So a music tagging model trained on a standard data set has seen about 300 times more data than a separation model trained on MuseDB18, but the sheer size of the data isn't the only thing that's nice about music taggers. It's that these instrument tags are way more diverse than what MuseDB18 supports. With standard music tagging data sets, the resultant models have seen up to 16 types of musical instruments compared to MuseDB's 4 source types. So great, music tagging, check. Now we'll talk about OpenAI's JUKEBOX. JUKEBOX is a generative model for audio. Specifically, it's a set of VQVAEs and transformers, although in this work, we're only going to use one of these VQVAEs. If you want more details, you could either read our paper or you can read the JUKEBOX paper. And because this is from OpenAI, we know they're going to do everything bigger and better. So through the use of high-powered computers and even higher-powered lawyers, they were able to train JUKEBOX on 1.2 million songs. And I really can't help myself here, so let me just show you one more animated bar chart. So here's our friendly neighborhood music separation data sets and music tagging data sets. And then I'm just going to throw JUKEBOX's data to the next, to the left of it or to the right of it. And it just leaves these other data sets in the dust. Okay, so JUKEBOX has seen a whole lot of data. Orders of magnitude more data than any other separation model has. So let's see how TagBox brings these 2 pieces together. The core idea behind TagBox is simple. When audio of an isolated source like the solo bass guitar is input into a music tagger, only the instrument tags corresponding to the bass source should be active. Therefore, what we're going to do is we're going to fix this set of predefined tags corresponding to our bass source, for example, and then pass a mixture through JUKEBOX, and then we're going to iteratively optimize the output of JUKEBOX until it matches those tags. With TagBox, we're going to run this optimization on each audio file individually. So let me just dive into this in a little bit more detail. First, we're going to put the mixture into JUKEBOX's encoder and get a location in its embedding space. Then we're going to decode this location back into audio. We're then going to use this JUKEBOX decoded audio to apply a mask to the input mixture. And this is going to keep JUKEBOX from generating audio wildly because we're restricting JUKEBOX to only removing audio information from the input mix. We're then going to pass this masked audio into the music tagger and to compute a loss between the current tags and our predefined source tags. We're going to use that loss to guide gradient ascent in the embedding space of JUKEBOX. We're going to do this over and over again until we're satisfied with the output. So the cool thing about TagBox is that we don't update the weights of either model. We're only going to update the location of the embedding space, but the tagger and the rest of JUKEBOX are completely frozen. Also, neither JUKEBOX nor the music tagger have ever been trained to do source separation, yet with this setup, it works. And this is all without access to data with paired mix and source data like a typical source separation network might see. So now I'm going to compare JUKEBOX to an older algorithm, RevitSim, as a baseline. And you'll notice that repSyn is a vocal separation algorithm, so all these other source types are completely undefined. Yet TagBox can provide separation estimates at about the same level of quality for all of the sources that we test across two different datasets, MuseDB and Slack. So now we're going to compare TagBox to a state-of-the-art purpose-built supervised separation system, Demucs, and unsurprisingly, this does remarkably well, except for when it doesn't have training data, like for this guitar, piano, or string sources from Slack 2100. And again, unsurprisingly, Demucs beats TagBox and all the sources that Demucs was trained on. But again, TagBox can provide separation estimates for all of the sources. In fact, TagBox was the only system that we tested that was able to provide source estimates for all of the sources in both data sets. So this is all good and well, but let's listen to some output from TagBox. This first example is this popular Oasis song. And here I've asked TagBox to separate vocals by setting the vocals tags. So TagBox can be finicky sometimes, but it seems to do best on these really sparse examples, like with just a mix of a guitar and a singer. Anyway, here's Wonderwall.
Today is gonna be the day that they're gonna throw it back to you. By now, you should have somehow realized what you gotta do.
And now here's the output from TagBox.
Today is gonna be the day that they're gonna throw it back to you. By now, you should have somehow realized what you gotta do.
Here's a second example of a violin and piano duet. Here I asked TagBox to separate the violin, and while TagBox doesn't seem to do as well here, to my ears, it feels like it's doing a pretty okay separation. So here's the mixture. And here's the TagBox optimization for the string tags. Okay, so that's TagBox. And with TagBox, we repurposed a generative model and analysis model and coerced them into doing source separation without retraining either one. This, again, is another project showing off the symbiosis of generative modeling and musical scene analysis. If you want to know more, I'll be presenting TagBox next month at ICASP. So finally, I want to talk about the last source separation project, which I'm calling NADE Separation. And this applies the generative modeling idea of autoregressive sampling to learn the interdependencies between different sources. In an auditory scene, musical sources are highly coordinated. Musicians create sounds that are designed to overlap in time and frequency content. So think rhythm and harmony. These interdependencies can make it difficult when we want to isolate audio from a particular instrument, such as in source separation. However, most music separation systems treat each source independently. These systems are only conditioned on the mixture, ignoring any dependencies that might occur between sources. Some systems further crystallize this as a hard prior into the design by training one network per source. But what if we want to model these interdependent sources? So, well, let's look again at generative modeling for some inspiration about how we can learn such dependencies. A common technique in generative modeling is autoregression. The way we set up autoregression in audio is typically by conditioning the model on previous time steps when it estimates the next time steps. This is how wave networks, for example, given information about the past, predict the next audio samples that occur in the future. In this way, the model learns the relationship between dependencies in time. So when we think about source separation again, these sources in music are interdependent. If we want to do some autoregression style learning to learn these dependencies between sources, we don't want to set up our autoregression in time, just like we saw in WaveNet. Instead, we want to autoregress along this source dimension. If we can do this, then we can use autoregression to learn these inter-source dependencies, but there's a problem. Unlike the arrow of time, which flows from the past to the future, there's really no natural ordering of the sources in a mixture. Does the bass come first or does it come last? What about the guitar? Is that first, second, third, fourth, the singer? I don't know. So how do we learn these conditional dependencies between sources with autoregression? And this is what an orderless NADE is designed to do. NADE stands for Neural Autoregressive Density Estimator, and it is designed to learn the dependencies between things where there's no natural order. Thus, a system trained like this can learn these intersourced relationships. So to do this, we'll need a special training setup. We're going to alter a multi-source network so that it has inputs for the sources, and for each training iteration, we're going to condition on a random subset of the input source data. Then, during inference, we can run a sampling procedure called a block Gibbs sampling to iteratively refine the set of initial estimates. I'm going to dive into both of these in a second, so let me first dive into how training works with NADE. Here's an overview of training. Like I said, we've altered the network so that it has additional input slots for sources in addition to the standard input for the mixture. At each training iteration, we randomly choose a subset of these input sources to make unavailable, which is a process we call masking. The network's loss is then computed only on the output sources that are masked. This forces the network to learn these dependencies. I want to pause here and dig into how orderless NADE autoregression relates to the typical time-based autoregression I showed you a few slides ago. So whereas in time-based autoregression, we condition on the past to predict the future, here we're going to condition on these unmasked sources to predict the masked ones. So we've inherently created an ordering where unmasked comes before masked. And the trick is we randomly set which sources are masked and unmasked at every iteration so that the network has to learn all possible orderings. This is why it's called an orderless system, but a better name might be like an omni-order system or an all-ordered system. But this paper is from almost 10 years ago now, and I'm not about to go dig up the authors and yell at them. So this is how autoregression happens in the source dimension and not the time dimension. So one final note is this means that we're unconstrained about the network architecture we use. It can input a full waveform or a spectrogram because the autoregression is on the source dimension and not the time dimension. So now we're going to turn to how the inference setup works. For the NADE separation systems, we can also run a sampling procedure in a similar manner to a generative model. Here, we're going to propose to use a block Gibbs sampling procedure, which looks like this. At the first step, all of the input sources are masked. And this is a typical source separation setup where we only have the mix as input. The network is then going to make its first set of estimates for each of the sources. And then we're going to put these initial estimates into the input slots for the next iteration. Just like in training, we're going to randomly apply masks to these input sources. And from this step, we're only going to keep output from the source slots that are masked. For the unmasked sources, we're going to carry over the source estimates from the previous step. You can see how this mirrors the orderless NADE training. And what's cool here is that we can use the initial source estimates to iteratively refine the estimates as we do more and more Gibbs steps. So the hope is that the initial estimates from step 1 get better and better as the sampling procedure progresses. Okay, so now let me show you some experimental results. In these results, we compare state-of-the-art separation network Demucs, and we compare the standard network way of training the network to our NADE training and Gibbs sampling. At inference time, we're going to evaluate the performance of the system with respect to the number of Gibbs steps, and we're going to look at the Slack and UCB datasets that I talked about before. So before I show you all of the results, let me just show you how to read these graphs. And each graph I'm going to show you represents just a single source, and higher values are better. This dotted horizontal line is the standard training, and the changing line is our model. The x-axis on each of these plots is the number of Gibbs steps, and that is logarithmically spaced. And the top number indicates the max improvement of our NADE training, and that's the number next to the title of the source. So here are the results on all 4 sources from the Slack dataset. We can see that in 3 of the 4 cases, more Gibbs steps monotomically produces better source estimates. The only source where it doesn't do that is in the drum source, and that is hard to tell from this graph, but that is already so high that it's hard to understand how a network could be better at separating drums here. And on the MuseDB 18 dataset, the performance boost is most pronounced in the vocals, which see a monatomic increase with more Gibbs steps. The other sources don't see as dramatic as improvement as the previous dataset, but they start at a much higher point, which indicates that orderless NADE training is itself beneficial. So that's NADE separation, where again, we borrowed ideas from generative modeling to learn these interdependencies between different sources. And I'll also be presenting this at ICAST if there's not enough time for questions here. So in this talk, I presented 4 recent projects that all marry aspects of generative modeling and musical scene analysis. DDSP is a generative model that enables realistic synthesis and expressive control. MT3 enables better transcription performance of more instrument types by using an encoder-decoder transformer. TagBox repurposes a generative audio model and a music tagger to do source separation without retraining either model. And finally, NADE Separation uses autoregression to learn the interdependencies between these sources when doing source separation. I hope I've made a convincing argument that there's a lot of room for cross-pollination between the areas of generative modeling and musical scene analysis, and I'm looking forward to seeing how new insights can empower the next generation of musical instruments. And on that note, I want to tie this all back into enabling musicians with new technology. So all of the projects I just discussed are good and well, but it's hard to see how they can affect the creative processes of everyday musicians if these ideas are stuck behind densely written academic papers and GitHub repos that are hard to run and all that sort of stuff. So my lab mates and I decided to add support for running deep learning models in the widely popular open source DAW Audacity. So we're currently working with the developers of Audacity to get this working in the main, get this shipping with the main build. But adding models in Audacity is easy, and the process is currently open to anyone who develops deep learning models in PyTorch. So if you have any PyTorch model that you have laying around and you want to bring it to musicians, podcasters, or audio creatives of any kind, you can check out this URL on the screen to learn more. And finally, I want to thank all of my brilliant friends, collaborators, and mentors, without whom none of this work would have been possible. And thank you so much for watching. Special thanks to Elio, Sertan, and Ken for inviting me and organizing this talk series. Links for all of these projects are on the screen, and you can find me at the usual places online. Thanks so much.